So, what does an atom actually look like? We all have this picture in our heads, right? But what if I told you that picture is completely wrong? The real story is way more interesting. It's like a scientific detective mystery that unfolds over 2 centuries, with each clue revealing a universe that's stranger and honestly more beautiful than we ever imagined.
Okay, be honest. When you picture an atom, is this the image that pops into your head? You know, this neat little solar system with a nucleus as the sun and these tiny electrons whizzing around it like planets. I mean, it's the symbol of the atomic age, it's on a million company logos, and it's pretty much what most of us were taught. But is it right? Well, the short answer is no, not even close. The truth is, the journey to understand what an atom looks like wasn't some straight line to the answer. It was a proper detective story, full of clues, red herrings, and a few shocking plot twists that literally forced scientists to rewrite the fundamental laws of physics. So, let's follow the evidence.
Our story kicks off in the early 1800s. Back then, the whole idea of an atom was just this ancient philosophical concept. It took a chemist, a guy named John Dalton, to find the first real piece of physical evidence that turned the atom from a neat idea into a hard scientific reality.
Now, Dalton was really fascinated by how chemical elements combine to make different compounds. And that word atom, it comes from the ancient Greek word for uncuttable. Dalton's big idea was that if all matter was made of these tiny fundamental uncuttable units, it would perfectly explain a really strange pattern he kept seeing in his experiments.
And here's the clue that cracked the whole case for him. It was a simple ratio. He was looking at tin oxides, and he saw that for a certain amount of tin, one compound had a specific amount of oxygen, while another one had exactly twice as much. This perfect 1-to-2 ratio, that couldn't be a coincidence. It was like a fingerprint, proof that atoms were combining in clean whole numbers. Matter had to be made of individual building blocks.
So for almost a century, Dalton's uncuttable atom was the bedrock of chemistry. It just worked. But then, a new discovery came along that was about to change everything. It turns out, the atom wasn't the end of the line. It had smaller parts inside of it.
In 1897, a physicist named J.J. Thomson was doing these experiments with cathode rays, and he found out they were made of particles. But these particles, which we now call electrons, were unbelievably tiny, negatively charged, and way lighter than even the smallest atom. The uncuttable atom had just been cracked wide open. This discovery, as amazing as it was, immediately created a brand new puzzle for our scientific detectives. See, atoms are electrically neutral. So, if they've got these little negative electrons inside them, there has to be some kind of positive charge in there to balance it all out. But where was it? And what did it look like?
Thomson made the first really good guess. He came up with what we now call the plum pudding model. Just imagine a kind of vague cloud of positive charge, and then the negative electrons are just scattered throughout it, like plums in a pudding. It was a perfectly logical model. It accounted for all the evidence they had at the time, until, of course, the next big clue came along.
And this next chapter of our story completely blows that plum pudding model out of the water. It comes from this absolutely ingenious experiment run by a scientist named Ernest Rutherford and his team.
The setup was brilliant in its simplicity. They decided to fire these tiny, positively charged things, called alpha particles, at a sheet of gold foil that was so thin it was just a few thousand atoms thick. Now, if the plum pudding model was right, the positive charge in those gold atoms would be way too spread out to do anything. The particles should have just zipped right through, and most of them did. But, and this is the huge but, a tiny fraction, about 1 in 8,000, bounced almost straight back, as if they'd hit a solid wall.
Rutherford himself captured the pure shock of this result. He later said, "It was as if you had fired a 15-inch shell at a piece of tissue paper and it came back and hit you." I mean, can you imagine? It meant something inside that atom had to be incredibly small, incredibly dense, and positively charged.
So Rutherford's conclusion was just staggering. He figured out that over 99.9% of the atom's mass and all of its positive charge was crammed into this impossibly tiny point right at the center, the nucleus. The electrons, they were somewhere out in the vast emptiness around it. The atom, it turned out, was almost entirely empty space.
So, we finally arrived at that familiar planetary model, a tiny, heavy nucleus with electrons orbiting it. But this model, which was born from Rutherford's incredible discovery, had a fatal flaw, a problem so deep it seemed to violate the known laws of physics.
So here's the brand new puzzle. According to all the physics they knew at the time, an orbiting charged particle, like an electron, should be constantly giving off energy. If it's losing energy, it should slow down, spiral into the nucleus, and the entire atom should collapse in a fraction of a second. But atoms don't collapse. We exist. So why not?
The solution came from Niels Bohr, and it was absolutely revolutionary. He basically proposed that the tiny world of the atom just doesn't play by the normal rules. Instead, he said, electrons are restricted to certain allowed orbits, or energy levels. Think of it like a staircase. You can be on step 1 or step 2, but you can't just hover in between the steps. And by jumping between these fixed orbits, they absorb or spit out light of very specific colors, which perfectly explained these things called spectral lines that had been puzzling scientists for decades.
Bohr's model was a total stroke of genius. It saved the atom from collapsing and it explained those spectra beautifully. But it was a hack. It was a brilliant patch, a special set of rules tacked on to the old physics. It worked perfectly for a super simple atom like hydrogen, which only has one electron. But the moment you tried to use it to describe anything more complicated, the whole thing just fell apart. The final piece of the puzzle was still missing.
Okay, to truly solve the mystery of the atom, scientists had to take an even bigger, crazier leap. They had to completely abandon the idea of an electron as a tiny little ball following a nice, predictable path, and instead embrace the truly bizarre world of quantum mechanics.
And this right here is the final mind-bending shift in thinking. We have to stop thinking about orbits and start thinking about orbitals. See, an orbit is a path. An orbital is not. Because of quantum rules like Heisenberg's uncertainty principle, we literally can't know an electron's precise location and its momentum at the same time. The electron doesn't exist at a single point, it exists as a cloud of probability, a kind of standing wave that's smeared out in space.
So what the heck is an atomic orbital, really? It's the modern answer to our big question. It's a mathematical description of a three-dimensional space around the nucleus. Think of it as a map of probabilities. It doesn't tell you where the electron is, it tells you where it's most likely to be found. This is the true shape of an atom.
And here's the really cool part. These probability maps have distinct shapes. The lowest energy orbital, the s orbital, is a perfect sphere. But as electrons get more energy, they start to occupy these more complex and beautiful shapes. P orbitals that look like dumbbells, and D and F orbitals that look like clovers or even more intricate patterns. And remember, these beautiful shapes aren't the paths the electrons take. They are the shapes of the electron itself, existing as a wave of potential.
And that journey brings us to one last, mind-bending thought. We went from a solid, uncuttable ball to a plum pudding to a tiny solar system, and we've landed on a nucleus surrounded by these shimmering clouds of probability. So if this is reality, if the very foundation of the matter you and I are made of is over 99.9% empty space, all governed by the laws of chance, then what does it even mean for anything to be solid? The answer, it turns out, lies not in the particles themselves, but in the powerful forces and energy fields between them. And it's a question that really shows just how deep, strange, and beautiful the atomic world truly is.